Hello and welcome, my future doctors and engineers. So glad you're here for this quick revision explainer on the thermal properties of matter. This is a super important chapter for both NEET and JEE, so let's get right into it and absolutely master these concepts. You see things every day and probably don't think much about them. Like, why are there these little gaps between railway tracks? And why does the steam from your hot cup of chai always rise up? Well, guess what? The answers are all about physics, specifically the thermal properties of matter. And by the end of this session, you're going to know exactly why. So let's break it all down, starting from the very beginning.
Okay, first things first. Before we can get into the cool stuff, we have to make sure our foundations are rock solid. The two most basic words in this whole chapter are heat and temperature. Now, a lot of people use them interchangeably, but in physics, nope. They are totally different things. Let's see how.
Let's really nail this difference down. Picture a giant bucket of water. Heat is like the total amount of energy in that entire bucket. Temperature, on the other hand, is like a measure of the average energy of the particles. Think of it as how hot or cold it feels. Heat is the cause, it's the energy you transfer. Temperature is the effect, it's what you measure. So heat is measured in joules because it's energy, while temperature is measured in Kelvin or Celsius. Simple, right? All right, now that we've got the basics sorted, let's jump into our first big concept, thermal expansion. And yup, this is directly connected to our railway track question. So what actually happens when you heat something up? It's actually pretty intuitive. When you give energy or heat to most things, their tiny particles get super excited. They start vibrating and moving around faster, and they start pushing each other further apart. The result? The whole object gets bigger. It expands. This can happen in just one dimension, like its length. We call that linear expansion. It can happen to its surface. That's area expansion. Or the whole thing can puff up, which we call volume expansion. Okay, pens out. You absolutely need to star this formula in your notes. It's so important for your exams. This is the one for linear expansion. So delta L is just the change in length. L is the original length you started with. Delta T is the change in temperature. And that Greek letter alpha is the coefficient of linear expansion. And that alpha, well, it's just a number that depends on what material you're talking about. And check this out. This table really shows you that different materials expand by different amounts. Just look at the value for Pyrex glass. It's tiny compared to steel or copper. And that low expansion is exactly why you can pour boiling hot water into a Pyrex dish and it won't crack. But a normal glass might just shatter. Cool, right? And that brings us right back to our first mystery. Railway tracks are just really long rods of steel. So in the scorching summer heat, what do? They expand. They get longer. Now, if there were no gaps, they'd push against each other with a massive force, creating something called thermal stress, and they'd bend and buckle. That would be a huge disaster. So those gaps are there for a reason, to give the tracks a little room to breathe or expand safely. So we know that adding heat changes temperature. But the next obvious question is, how much heat does it take to change the temperature by, let's say, 1 degree? This idea is where we get into heat capacity and calorimetry. And here it is, another 5-star formula for all your numerical problems. Q equals ms delta T. Q is the heat you supply, m is the mass of your object, delta T is how much you want the temperature to change, and S, that's the hero here. S is the specific heat capacity. It basically tells you how stubborn a material is when it comes to changing its temperature. And which substance has a ridiculously high specific heat capacity? You guessed it, water. 4186 joules per kilogram per Kelvin. That's a huge number. It means water can soak up a ton of heat without its own temperature shooting up. And that's exactly why we use it as a coolant in car engines, and why a hot water bag feels warm for such a long time. It's great at storing heat. This right here is the golden rule of calorimetry. It is the foundation for pretty much every problem you'll solve on this topic. If you mix something hot with something cold in a perfectly insulated box, like a calorimeter, no heat can escape. So all the heat that the hot object loses is perfectly absorbed by the cold object until they both reach the same final temperature. Heat lost equals heat gained. You have to remember this. Okay, but what about this weird situation? What happens when you keep pumping heat into something, like a block of ice, but you look at the thermometer and the temperature just stops rising? It's stuck. Where is all that energy going? Well, it's going into a change of state. This mysterious, hidden heat has a name. It's called latent heat. It's the energy that's used not to raise the temperature, but to break the bonds between molecules and change the entire phase of the substance, from solid to liquid at its melting point or from liquid to gas at its boiling point. The whole time this is happening, the temperature stays totally constant. And thankfully, the formula for this is super simple. Q equals m times L. Q is the heat, m is the mass, and L is the latent heat for that specific substance. We just use a little F for fusion, which is melting, and a little V for vaporization, which is boiling. Let's see how you use all this in a classic problem. Imagine taking a chunk of ice from below freezing all the way up to steam. It's a journey, right? And it happens in stages. First, you're going to use Q equals ms delta T to heat the ice up to 0 degrees. Then, at 0 degrees, you'll use Q equals mLF to melt all that ice into water. Step 3, you're back to Q equals ms delta T to heat that water all the way up to 100, and finally, you use Q equals mLV to boil that water into steam. You just calculate the heat for each step and then add it all up for the grand total. Okay, we've talked a lot about what heat is and what it does, but how does it actually travel from one place to another? How does heat from the sun get all the way to us? And this, my friends, finally brings us to our second question from the very beginning. Why does steam from your chai rise upwards? So there are 3 main ways that heat gets around. The first is conduction. This is heat transfer through direct touch, like when you grab a hot pan and the handle gets hot. The second is convection. This happens in fluids, like air or water, when the hot stuff literally moves from one place to another. And the third is radiation, which is heat traveling as waves. This one's special because it doesn't need any medium at all. It's how the sun's heat travels through the vacuum of space to reach us. And there you have it, the answer to our chai question. It's all about convection. The air right above your hot tea gets heated up. Hot air is less dense, it's lighter, so it starts to rise. Then the cooler, denser air from the sides swoops in to take its place, it gets heated up, and it rises too. This creates a continuous circulating current, and that's exactly what you see as the rising steam. Now, going back to conduction for a second, for all you problem solvers, when you get questions about heat flowing through a metal rod or a slab, this is the formula you'll need. H is the rate of heat flow, basically how fast heat is moving. It's equal to K, the thermal conductivity of the material, times A, the cross-sectional area, times the temperature difference between the hot and cold ends, all divided by the length, L. Whew, okay, that was a whirlwind tour, but we have officially covered all the core concepts of this chapter. Now for what might be the most important part of any revision session, a super fast, rapid-fire recap of all the key formulas we just talked about. Are you ready? Here they are, your absolute exam essentials. Think of this as your cheat sheet. When things get longer because they're hot, use the linear expansion formula. When the temperature is changing, you use the specific heat formula. When the state is changing, melting, boiling, you go for latent heat. And when heat is flowing through a solid, you use the conduction formula. Go on, take a screenshot. These are your best friends for the exam. Okay, time to put your brain to work. Here is a fantastic practice problem for you. It's tricky because it combines what we learned today about thermal expansion with concepts from mechanical properties of solids, like Young's modulus. This is a perfect NEET and JEE level question. So pause the explainer right here, give it a serious try, and then drop your answer in the comments below. And that is a wrap on our quick revision of thermal properties of matter. I really hope this explainer helped clear things up and made these concepts stick. If it did, do me a favor and smash that like button, share it with your friends who might need it, and of course, subscribe for more quick revision explainers just like this one. All the very best for your exams. You've got this. Keep learning.